Hello everyone. In this lecture, I shall discuss the consistency and solution of a system of linear equations. You are given a system of linear equations, right? a11 x1 plus a12 x2 plus a1 and xn. So this system of linear equations. So how many unknowns? How many unknowns? N unknowns. And how many equations? And how many equations? 1, 2, 3 up to m. So it is in m. It is having m equations and n unknowns. Okay, so this m may equal n, m may greater than n, m may less than n, no issue, right? If m is equal to n, then the system is determined, right? If m is greater than n, then the system is, you have more equations. Okay, you have more equations, so the system is over-determined. Here it is over-determined. If m is less than n, okay, the number of equation is less, means it is under-determined. Okay, so according to the different situations, we will see what will be the consistency. So now this is a system having m equations and n unknowns. M equations up to m and n unknowns. Starting from x1 to xn, we have n unknowns. Now if you want to write it in matrix form, okay, I just collect the coefficients. So here this matrix is called my coefficient matrix, and then I collect the unknowns, x1, x2, xn. I collect the unknowns. This is my unknown vector. Okay, this is my unknown vector, and this is my coefficient matrix. A is my coefficient matrix, and this right hand side b is called my constant vector. Okay, so now in short I write ax is equal to b, where a is the coefficient matrix, b is the constant vector, and a together with b. If I combine a, the coefficient, together with my right hand side, this is called a augmented matrix. Okay, augmented matrix means by applying the properties of row eliminations here, row operations here. Okay, simultaneously we are operating the left hand side and the right hand side. Okay, so already I have told you in Gauss elimination method, and we adopt the back substitution technique to get back to the solution. Now there arise two cases. One is case 1, if this right hand side b1, b2, bm is not equal to 0, then the system is a non-homogeneous system. The system is a non-homogeneous system. And if this right hand side is equal to 0, then the system is a homogeneous system. Okay, so now we will discuss the solution under both cases. You note that if a system is homogeneous, then what will happen? If I put x1, x2, xn all 0, then all the equations are satisfied. Then definitely we must have a solution, right? We must have a solution. But in non-homogeneous system, it may not have a solution, as we see in Gauss elimination technique. So let us discuss the details under what conditions the solution will exist and whenever this doesn't exist. If at all the solution is exist, then the system is called the homogeneous, the system is called the consistent. If the solution doesn't exist, then it leads to inconsistency. So now the homogeneous system is always consistent. Okay, so let us see the individual cases in view of the rank of the matrix. Now recalling my earlier lectures on Gauss elimination and rank, suppose there arise the situations 2, 3, 5, 4, 0, 2, 6, 0, 0, 7, and the right hand side is my suppose 5, 0, 4. A situation may arise like this. 2, 3, 5, 0, 1, 2, and it is 0, 0, 0. It is 3, 5, 0. The situation may arise like this. Or the situation may arise like this. Suppose it is 2, 3, 5, 0, 2, 6, 0, 0, 4, and it is my 3, 1, 0. A situation may arise like this. So in first case, you see here, suppose xyz is my variable, is 7z is equal to my 4. 7z is equal to my 4. As you see here this is my A, this is my A, up to this is my A, and this up to this it is my augmented matrix AB, is not it? And similarly in each case. So what will happen here, as we recall, this lead to 7z is equal to 4, this lead to unique solution, already we have seen in my first lecture of Gauss elimination. So now the question is here, if in view of my A, what is the rank of A here? It is already in the triangular form, upper triangular form, the number of non-zero. So what is my rank of A? What is my rank of A? So rank of A is my 3 here. If I see this total, if I see this total AB, if I see how many non-zero? This is 1, this is 2, and this is 3. So this is same as rank of this is same as rank of the augmented matrix. So in this case we see here rank A is equal to rank AB. So here likewise, what is your rank of A? Rank of A is 2, rank of A is your 2, and what happens to rank of B? Rank of AB? Rank of AB is also my 2, right? Number of non-zero row in whole AB, it is also 2. Rank of AB, rank of my AB, is not it? Now what happens to the third case? In the third case, what is your rank of A? Rank of A is 3. Here rank of A is 3. But what happens to your rank of AB, the total AB here? The rank of AB is, this is 1 non-zero row, this is 1 another non-zero row, but this is a 0, this is a another. Make a small correction here. You make it 0, you make it 0 and you make it 4. Okay, you make it 0 and make it 4. So what will happen here? Now what is the rank of A in view of this part? In view of this part, my number of non-zero row is 2, but in view of this entire part, the number of non-zero row is 3. So which is less than rank of AB. Or in general I can say here, rank A is not equal to my rank AB, right? Rank of the coefficient matrix is not equal to the rank of the augmented matrix. But in both this case, in these two cases, what I see, rank of A is same thing as rank of AB, If this will happen, right? If this will happen, then this unique solution is here, and here infinite solution is here. Right? Infinite solution is here, and here there is no solution. Why? Because 0 is equal to 4 is impossible here, right? Now if there is a unique solution or there is an infinite solution, means if at least one solution is there, then the system is consistent. Okay, then the system is consistent. Now the consistency system again it will be of two parts. There may be unique solution or there may be infinitely many solutions, but here the system is inconsistent, means 0 is equal to 4. Here it is, the system is inconsistent here. The system is inconsistent here. Okay, the system is inconsistent here. So the system, whenever the system is inconsistent, if rank of the coefficient matrix is not equal to the rank of the augmented matrix. But here in first case, what we see here? We see rank of coefficient matrix is same as the augmented matrix, is number of unknowns. But what we see here, the number of unknown is 3 here, but here it is smaller than the number of unknowns. Is not it? Number of unknowns. So what is our observation now? The system is consistent. If rank A is equal to rank AB, and it is unique solution if rank A is equal to rank AB is equal to number of unknowns. Okay, number of unknowns. And here what will happen? Here rank A is equal to rank AB is less than number of unknowns. Okay, number of unknowns. So now we summarize this. This is a important concept. This is a most important concept, okay, in system of equations. So let us summarize it. Now we summarize this. A system of equation Ax is equal to B is consistent if rank of the coefficient matrix is same as the rank of the argument matrix. Now whenever this rank A is rank AB is same as the number of unknown, then it leads to a unique solution. If it is smaller than number of unknowns, okay, smaller than number of unknowns, then it is an infinite solution. Whether it is unique solution or infinite solution, means there is a solution, means in this both the cases the system is called consistent. The system is consistent in both the cases. But here when rank A is not equal to rank AB, then in this case the system is inconsistent. Now this is the Rouché's theorem. Okay, so we don't bother about the theorem, just we should know the theme, how to recognize the system is consistent or not. Now coming about a homogeneous system. In a homogeneous system, a right hand side is always 0, right hand side is always 0. So therefore here x1 is equal to 0, x2 equal to 0. If I substitute all the variables at 0, xn is equal to 0, then it must be a solution or not? It is a trivial solution. So homogeneous solution always possesses trivial solution, right? So homogeneous system always possess a trivial solution, possesses a solution. Therefore it is always consistent. Right. Now the question is, apart from the trivial solution, is there any other solution? If at all, if any one of them, if at least any one of xi's, right, x1, x2, xn, if at least we get any one of them is not equal to 0, then the solution is trivial. Okay, you are asked to solve this problem, test the consistency of this following system and solve. Okay, so now you should write the augmented matrix as in the usual way. So coming to my solution, consider the augmented matrix means the coefficient matrix. Here it is 1 1 2 1 1 2, and it is 1 minus 1 2, it is 3 1 1, and you should also write the right hand side, it is my 6 5 8. Okay, so this is my augmented matrix. Now we apply the row operation to this matrix to bring it into a upper triangular form. Okay, so let me to recall you the elementary row operation. Already I have told you in my earlier 2 lectures in Gauss elimination as well as in rank. So my elementary row operation, I have already told you we can interchange any two row, right? Second, we can replace a row by a non-zero constant multiple of the same row, that non-zero constant. And third, we can increase the row, or we can decrease the row by a constant multiple of any other row. And in view of here property number 2, if a constant is multiplied here, then there is also no harm. Now this is a powerful property to evaluate it. So now here k1 and k2 is not equal to 0. So on the basis of this we are going to solve it. So apply elementary row operations here. Okay, so we want to bring this position 0 and we want to bring this position 0. So what we have to do, So your R2 is simply replaced by R2 minus R1. It is 1 minus 1. 1 minus 1 means throughout this row we have to carry out the operation, not that for the single place here. Okay. Similarly R3, here it is 3, here it is 1. If I multiply 3 with row 1 and subtract it from row 3, so it is my R3 minus 3R1. Okay. So here R1 remains silent, no change in R1, and in R2 is simply R1 minus R2 minus R1. So 1 minus 1 is 0 here, it is minus 2 here, it is 0 here, it is minus 1 here. In question actually it is here Z only. So this is here 1 here, this is here 1 here. So this will be here. Okay, so this is here 1, so this will be here 1. 2 minus 1 is 1. Now coming to R3 minus 3R1, it will give you 0, minus 2, 1 minus 3 minus 2, and it is minus 2, and it is here minus 10. Just separate it by a dotted line. So now again what we have to do, we use this position to make this position 0 here. Okay, so what we have to do is, here R3 is replaced by R3 minus R1 simply. So row 1 remains silent, 1 1 2 6, row 2 remains silent, 1 minus 1, and simply we subtract it. It is my 0 here, it is my 0 here, it is my minus 3, and it is my minus 9. Okay, minus 9. So now we are ready to solve it. Last row involves only one variable. Okay, so by my back substitution, you see I use my back substitution here, back substitution. So before do that, to get the solutions, I must declare it here, the consistency of the system. So what is the rank of this matrix A? So rank of A is equal to clearly rank of A is equal to my 3. And what happens to my rank of AB? Number of non-zero row in AB also 3. So this is equal to my rank of AB. So this implies the system is consistent. And also it is equal to number of unknowns. Okay, number of unknowns here, number of variables here is 3. So the system is consistent and provides unique solutions. Okay, because it is same as the number of unknowns. Now come to the solution part. By back substitution method we will solve it. We write the last row here, minus 3z is equal to minus 9, and coming to the middle row here, minus 2y plus here z is equal to minus 1. Then first row is here x plus y plus 2z is equal to here 6. So row 1 will give you, so this implies you will get, if you solve it, what you will get, here z is equal to 3 here. Now if you substitute the value of z here, we will get the value of y. So here y will be 2 here, y will be 2 here. Then you substitute both y and z here, and it will give you x here, is not it? So here x will be 6 minus y minus 2z. You substitute the value here. So you substitute the value here. So actually this is here 1. This is here 1. So this is z. So this will be here 6 minus 2 minus 3 is here 1. So therefore what we are getting? Therefore we are getting x is equal to 1, y is equal to 2, and z is equal to 3. Just to get it confirmed that the answer is true, we may just verify here. We just substitute here to check whether putting x, y and z, whether these equations are satisfying or not. To be in safe side that our answer is correct, we should check a brief check on this. Okay, so now coming to another example, coming to another important problem. Find the value of some parameters lambda and mu such that this system possesses unique solution infinite solution and no solutions. Okay, so as usual we should solve it. Consider the augmented matrix. Is my AB. So what is my augmented matrix here? I consider the coefficients 1 1 1, right hand side is 6, it is my 1 2 3, right hand side is 10. It is in the last equations. Here you have a lambda and mu here, so it is 1 1 lambda and mu. Okay, so as usual we adopt the technique of row operations to bring it to a upper triangular matrix, Okay, so my simply R2, it is 1 here, it is 1 here, it is 1 and 1 here, so you simply subtract it. R2 is replaced by R2 minus R1 and R3 is replaced by also here R3 minus R1. Actually this is here 2y, so this is 2y. So now it is first row remains silent, 1 1 1 6. Second row will be here 0 1 2 4. Third row will be 1 minus 1 is 0 here, 2 minus 1 is 1 here, and it is my lambda minus 1, it is my mu minus 6. Okay, mu minus 6. Now again next step we have to bring this position 0 by using this. Okay, we have to bring it 0. So here R3 is replaced by simply R3 minus R2. Now row 1 remains silent, 1 1 1 6. Row 2 is here 0 1 2 4, and what happens to your last row? It is 0, it is lambda minus 3, then it is here mu minus 10. Okay, so now this is my final step here. Now we see for individual cases here. So for case 1 you see we have unique solution. For unique solution what do we need? So this must be not equal to 0, then we will get the rank of this is 0. Now this may 0 or may not 0, we don't bother, but this is not equal to 0 for your case 1, is not it? That means for unique solution your lambda is not equal to 3. But what happens to mu? Mu may 10, may not 10, that doesn't matter. Mu is arbitrary. Is not it? Now what will happen under case 2? For infinite solution, what will happen? For infinite solution we have rank of A is rank of AB and is less than 3, because number of unknown is 3 here, number of unknown, number of variable. So here you see, to make this less than 3, it must be 0, and it must be 0. Then only you will find infinite solution, is not it? So we are getting here lambda minus 3 is equal to 0 and mu minus 10 is equal to 0. So this implies my lambda is equal to 3 and mu is equal to 10. Okay, so this under this case it will lead you to infinite solution. So for no solutions what do we need? We need that some contradiction should come out. So here if it is my 0 here and if it is my non-zero here, then it will lead me to no solution, is not it? So for no solution here rank of A is not equal to your rank of AB. For specific, if I make it this, okay, then what will happen? Rank A, suppose rank AB is my 3 and rank A is my 2 here. Then for rank A to 2 we need lambda minus 3 is 0. Lambda minus 3 is equal to 0. But here mu minus 10 is here not equal to 0, is not it? So that means my lambda is equal to 3 and mu not equal to 10. If this will happen, then it will lead you to no solution. So this is the case. So this is the case of the no solution. Okay, for no solution we have lambda 3 mu not equal to 10. For infinite solution we have lambda 3 mu 10, and for your unique solution lambda is not equal to 3 but mu is here arbitrary. So Actually, this lecture is in continuation to my earlier two lectures. In first lecture, I have told you the Gauss elimination method. In the second lecture, I have told you the rank of the matrix. Okay. So this lecture is in continuation to this. Unless you have knowledge of Gauss elimination and rank, you cannot get the thorough knowledge of this. So first you should see these two lectures. And one more thing. And in Gauss elimination technique, I have solved many examples where I have discussed the cases of infinite solution, cases of no solutions, cases of your unique solutions. So in those problems, you should adopt this Ruchi's theorem here, the consistency technique. Okay, you actually consistency was hidden, but here after this Ruchi's theorem, you can implement this consistency on the basis of your rank of the matrix. Okay, so this is all about the consistency of the solutions. For many problems you should see some standard book, and this my first lecture on Gauss elimination will also give you many examples. Let us close this lecture. So before closing this lecture, I request you here, if you find this lecture is useful to you and is interesting to you, you should subscribe to my channel, so that it will give me a motivation for uploading and preparing for the lectures. At the same time, you will also get the notification on your screen, so that whatever the next lecture will be uploaded, it will come to your screen. Okay, so thank you all. Have a nice day.